and Assalamu alaikum everyone. My name is Arsalan Farrukh and I teach math and physics. In this particular video, I will try and explain some fundamentals regarding differentiation and how we get the formula of differentiation, one of the very basic formula, and how to use that particular formula of differentiation. But first of all, I would want you to identify what is differentiation, what we actually do by the process of differentiation. So first of all, you need to sort of recall that, like, if you have a particular straight line and you know 2 points on that particular straight line, you can get yourself the gradient of that straight line or the slope of that straight line by applying the formula m equals y2 minus y1 over x2 minus x1. And you can also, interpret this as this is the change in y and this is the change in x. So, when we find out the gradient, what gradient actually represents is basically the rate of change of y with respect to x. But there is a very simple formula, and we can easily find out that rate of change of y with respect to x in cases where it's a straight line. It's a linear relationship, and you can easily find out the rate of change of y with respect to x, and you can identify that that particular rate of change is constant as well, which means a straight line will be representing a linear change. So if you consider any 2 points along that straight line and you apply the formula of rate of change, it is going to be same. You will still get the same rate of change. So the rate of change is going to be constant or uniform or same throughout. Process of differentiation is mainly applicable to situations where you are trying to find out the rate of change, but the rate of change is not constant. This happens when the variables are not linearly related, and on graph they are not represented by a straight line. Instead, they are represented by a curve. So the first thing that you should recognize is the fact that the rate of change of y with respect to x in this case is not uniform. It depends where you're considering it. So if you look at it closely, this graph is less steeper in the beginning, and then the steepness of the graph keeps on increasing. In other words, the rate of change is also increasing. The rate of change is not constant. So we can say the rate of change is dependent on x, or we can say that it is a function of x, and which is why we use the term gradient function. So instead of having a single constant value gradient, which is the case with a straight line, here we have a gradient function, which means that every different point will have a different gradient. So the process of differentiation helps us to find out that gradient function. To be able to understand that, first of all, try and have a look at it graphically. If there's a particular point P, which is represented by x and y, x is the x coordinate of that point and y is the y coordinate of that point, and I'm looking to find out the gradient of this function at this particular point P. Well, I just know this particular formula of gradient, and if I wish to apply that, and let's say I just take another point on this graph, and after taking that another point on the graph, I find out the gradient of this line segment. You can clearly see that the gradient of this line segment is a lot different from the gradient of the curve. But one thing you will notice, which is that if I take these points closer together, then this gradient keeps on getting more and more closer to the gradient of the curve. So if I keep on making these points closer and closer, and if I will just take 2 points which are barely separated from each other, they're very close together, and if I find out the gradient using those 2 points, that will be the gradient of the curve. So the thing is that the gradient of the line is not equal to the gradient of the curve. But if I take 2 points very close to each other, then the gradient of line tends to become equal to the gradient of the curve. So, I mean, and that's something you can do graphically as well, that if you would want to find out graphically the gradient at any particular point, you can draw a tangent and then find out the gradient of that particular tangent, which should represent the gradient of that particular curve at that point. But we are more interested in finding out the gradient function, which is basically a single function, and it's a more algebraic mathematical process where I should be able to find out more accurately the gradient function. But what we identify from here, that if we take a change in y over change in x, and this notation is for limit delta x approaching 0. That means that if we take delta y over delta x, but we make sure that the change in x is really small and it's nearly becoming 0, then that would be equal to gradient function. And we have a slightly different representation for that. Instead of writing this whole thing down, that we are finding out change in y over change in x. For change in x approaching 0, we write down dy by dx. So basically this is an alternate way of writing this down, which is basically an indication of the fact that this is the gradient function. So every time we are going to be looking at the gradient function, we are going to be representing that as dy by dx. Now let's see how we can find out that gradient function algebraically. Suppose that the equation of the curve is y is equal to x square, which is clearly not an equation of a straight line. And I'm trying to find out the gradient function of this particular curve. And the method by which we find out this gradient function is called the first principle method. Now, what we do is that we suppose that x undergoes a small change delta x, and the corresponding change in y is delta y. So just like x and y is lying on the graph, the new point, which is x plus delta x and y plus delta y, must also satisfy the equation of the curve. So in place of y, we can write y plus delta y, and in place of x, we can write x plus delta x. Now we're gonna open it up by using a formula, and we can say that a plus b whole square is equal to a square plus 2ab plus b square. Keeping in mind that delta x is the change in x and delta y is the change in y. And I will move this y from the left hand side to the right hand side of the equation. Reason being, I'm trying to find out delta y over delta x. So I will be making delta y the subject of equation. Now, when I move this y over here, and I recall that this y was originally x square, so in place of y, I can replace x square. And x square would cancel out. And after that, I will be left with two terms, 2x delta x plus delta x whole square. And from these two terms, I will take delta x as common. The reason I'm going to take delta x as common is because, again, I'm trying to find out delta y over delta x, and I can achieve that by taking delta x common and then cross multiplying it on the other side, which is what I do in the next step. When I cross multiply it on the other side, it becomes delta y over delta x equals 2x plus delta x. I would want to find delta y over delta x for a limit where delta x is very small and approaching 0. So I put the limit on both sides, and I realize that if delta x is really extremely small and is approaching 0, so I can approximate the right side of the equation by putting delta x as 0. And when I put delta x as 0, I will get myself 2x. Now when I put delta x as 0, I get myself dy by dx as 2x. What is the long process of finding out the gradient function? And what does this tell me? This tells me that this gradient function is clearly a function of x, and I can plug in any value of x to find out the gradient function at that specific point. So we got ourselves a formula which says that if y is equal to x square, then dy by dx must be equal to 2x. You can try it out on different situations. It will be the same thing. You can do it with x cube and you can do it with x power 4. Obviously your expansion is going to be longer, but it will always follow a certain pattern. If you notice over here, when it was y is equal to x square and when we differentiated it became 2x, so that means this power got multiplied and the original power got reduced by 1. So from here we can sort of identify, though that can also be proved, but if it was y is equal to x cube, then its dy by dx would be power being multiplied and then reducing the power by 1, and so on and so forth. So we get ourselves a formula for differentiation of x to the power n, which is going to be n x n minus 1. What you have to remember is that whatever is the power of x, it has to be constant, and that power gets multiplied in the coefficient and then the power gets reduced by 1. There are a few more things which are always applicable to differentiation. If you have two different terms, then you can apply the formula of differentiation to both the terms separately. And the other thing that I would want you to recognize is that if there's a constant multiplying, then that constant would be copied as it is, and just the variable part would be differentiated. So when I differentiate this particular equation, a is constant, that's copied as it is, and x to the power n differentiates as n. I multiply the power and then reduce the power by 1, so x to the power n minus 1. Similarly, b x to the power m differentiates to become b as it is, power m multiplies and the power of x reduces by 1, that is m minus 1. And one more thing, which is if you have a constant, some constant value, it could be 7, 10, 15, 8.5, whatever it is, but you have to understand, well, you can logically identify as well, that if something is constant, then its rate of change must be equal to 0. So if something is like, let's say y is equal to 8.5, so its rate of change is what? It's equal to 0. So, well, that's one way of looking at it. Another way is that if you have a constant, then that means that the power of x must be 0. And if you apply the formula of differentiation onto that, that is multiply power and reduce power by 1, it also becomes 0. So what are we getting from here? That any constant when differentiated is always going to become 0. Now let's have a look at few examples to see how this actually works. For example, you have to differentiate y is equal to 3x square minus 4. So you will differentiate this term separately and this term separately. So 3x square means 3 times 2x, and 4x means 1 times x to the power 0. And this simplifies as 6x and this simplifies as 4, and that's why the differentiation becomes 6x minus 4. Let's have a look at another example. I have to differentiate y is equal to 2x cubed minus 7x to the power 6. So 2 will be copied as it is, and x cubed will be differentiated to 3x square. Likewise, 7 will be copied as it is, and x to the power 6 would be differentiated to 6x to the power 5. And then we can simplify it to get ourselves the simplified result. Other thing that you must recognize is that this differentiation is only applicable to a polynomial. So if you get something like this, you're going to have to first open it up and simplify it and then apply differentiation. So if you have x times 2x plus 3, first you multiply it to make it become 2x squared plus 3x, and then x squared differentiates to 2x and x differentiates to 1, which is why it simplifies to 4x plus 3. Similarly, another thing that you need to identify is that the formula of differentiation is applicable to both negative powers as well as decimal powers, which is non-integer powers. Like if I have x squared minus x to the power minus 1, x squared would differentiate as 2x, and x to the power minus 1 would differentiate as minus x to the power minus 1 minus 1, which becomes x to the power minus 2, and that's how you get this result. And then you can simplify it in any form. Another thing that you must recognize is that this formula can be applied to non-integer powers as well. Like if you have x to the power half and x to the power minus 3 upon 2, then half would multiply and x power would reduce by half, which becomes x to the power minus half. And similarly, minus 3 upon 2 multiplies and minus 3 upon 2 reduces by 1 to become minus 5 upon 2. So in any situation, you can apply this formula with whatever power, but you just have to make sure that you write it down as a polynomial. So another example is when you have x cubed plus x squared divided by root x. First thing is that you're going to separate these two terms. So one term is going to be x cubed divided by root x, which is x power half, and the other one is going to be x squared divided by root x, which is also going to be x to the power half. And once you will be able to separate these two terms, you will obviously simplify, and 3 minus half becomes 5 over 2 and 2 minus half becomes 3 over 2. And then you will apply the differentiation formula. So dy by dx would be 5 over 2 multiplying and the power of x reducing by 1, which becomes 3 over 2. And similarly 3 over 2 multiplying and power of x reducing by 1, so 3 upon 2 minus 1 becomes half. We can rewrite x to the power 3 over 2 as x under root x and x to the power half as root x. So guys, this is how we apply a very basic formula of differentiation. I hope you understood the concept well. I would really appreciate if you'd like the video and share it and subscribe to my channel. Thank you.